Right, so let's get started. Welcome back for the second session on confidential computing. Let's welcome Ivan Puddu from ETH, who's going to talk us about their collaboration with ICRC.
Thanks for
Ivan.
the introduction, Marius. So yeah, as you mentioned, I'm going to talk about our SysJRC project, which is about building a sovereign cloud for the International Committee of the Red Cross. So I guess you unfortunately heard about the Red Cross in the news recently and about what they do, but just to recap what is relevant for this project. So as part of their core mission, they go around the world and to make sure that human rights are not being violated. So for instance, this is a poster from their website, and they go to prisons and they make sure that people are not being tortured, that they are being provided water, and basic human needs. So another thing they do, probably you cannot read it because it's a bit too small, but they also try to keep relatives in contact with their families, so they keep track of who is in which prison, or if people are crossing a border fleeing from a conflict, they try to keep track of which route they are taking. And they do that to minimize suffering. So another way that they would like to minimize suffering is to use this data as much as possible. For instance, to reconnect lost relatives. They would like to use machine learning and all kinds of things, if possible, to try to reconnect these people. However, they are not really IT experts, so they would like to offload some of this to the cloud, to kind of have a cloud service provider help them with building the infrastructure needed to support these functionalities. The problem that they have, however, is that as soon as they start storing data in the cloud, this data falls now under a different jurisdiction. So let's say that it's being stored in some server in Norway. Now a judge can subpoena this data there, and some people can enter the data center, for instance, to get this data. Or this data is highly sensitive and could be a target of intelligence agencies that have a lot of resources to throw at exfiltrating this. So particularly what is different for them is that they are concerned about lawful access to the data. And the reason for that is that it can impact their trustworthiness with the countries where they have access to. So if, I don't know, I'm Venezuela and I allow them to come and whatever, see my prisons, I would like them to be able to keep this data confidential. And as soon as this lawful access is a concrete risk, they might lose the relationship that they built with these countries. So yeah, this is not, unfortunately, just an academic exercise. They were recently hacked, and the data of Alpha Familia vulnerable people was exposed. Maybe I should say rather they weren't directly hacked. It was a company that they were paying to manage the data for them was hacked. So what is their attacker model concretely? They are worried about an attacker which has a lot of resources to pour into this, and that might have lawful access to the data that they are storing in the cloud. However, they have some advantages in the sense that they have some protections under international law. For instance, they have offices in Geneva, and not even the police can get into these offices if they wanted to. On top of that, we assume that their agents have some special protections, and they cannot be coerced to reveal data. And they trust some, at least hardware manufacturers, to make the hardware according to specification, but they don't necessarily trust these manufacturers after the hardware has been made. So a clear promise for them was, for instance, to use trusted execution environments, which I guess were mentioned a bit before today in Cedric's talk, but essentially they allow to build, to reduce the TCB and to not have to trust the operating system, for instance, and so to execute even in a potentially compromised environment. There are some drawbacks for this. For instance, they are still vulnerable to side channels, and you actually still need to trust a third party during this whole computation. Although it's not clear exactly for which things you have to trust a third party. So concretely, in terms of TEs, they do trust the manufacturers again to manufacture this properly, but they do not trust them at runtime. And they assume that the OS could be compromised. And so one of the initial questions were whether they could use SGX or SCV with this attacker model. So to explain, maybe a bit foreshadowing why they cannot do that, I'm going to briefly explain how attestation works in SGX. So let's say that, and attestation is one of these fundamental primitives that you need to make sure that your code is actually being protected in your trusted execution environment. And so the way this works is you have your code running in this SGX enclave, and this does local attestation to a so-called quoting enclave, which is an enclave developed by Intel running on your server on the cloud. Then this quoting enclave will do remote attestation, which is essentially taking the measurement of the code and then signing it with a private key, which is sent to the remote verifier, which in this case will be the ICRC. Now, the ICRC cannot really do anything with this blob. The only thing it can do is to send it to an Intel attestation service, and then this service will be like, okay, yeah, this private key actually is linked to a public key that we know belongs to a legitimate CPU, so trust us, you can trust this attestation quote. And in non-linkable mode, actually every time you get this attestation, this blob is different because the quoting enclave uses a different private key. So yeah, essentially if you're doing this, you have to trust Intel to tell you the right thing. And if Intel can be coerced or is mandated to lie to you, you have no way of knowing. So this could be basically what happens. Like, let's say that on your system now, on the server, your enclave is not actually running protected by SGX, but is being emulated. And so now Intel tells you, yes, this is fine, and you have no way of knowing. You have no way of distinguishing these two cases, basically. So luckily, this linkable mode exists, which essentially allows you to tell, okay, I saw this attestation before, and now I see it again. So if it's the same and the system was fine before, it will be fine now. And the way this is done is that this EPAD private key here, the same key it's used on every attestation request. And well, if you look a bit more into it, the way this works is you have the quoting enclave essentially stores the key on disk, and then it asks the CPU to generate another key to decrypt this private key. And so every time the quoting enclave is decrypting it, and then it's using this key to sign the remote attestation message. And it does that with a CPU instruction, which is called eget key. Now, it doesn't really matter exactly what this eget key does, but essentially what matters is that eget key only is a function of these green parts, and none of these green parts is actually the measurement of the enclave. So essentially what Intel can do, if it's malicious, it could just create a new quoting enclave that is not acting according to specification, and this enclave could leak this private key. So even if you're using linkable mode, so Intel is then asked to compromise your system, they could just deploy a new enclave there, and this enclave could provide fake attestation reports. The main point of what I'm trying to say is that so normally this SGX was designed with Intel being trusted. So Intel is considered trusted, and if that's the case during the whole computation, then you're fine. However, if Intel can be compelled to kind of create a special enclave just for your system, which you have no way of knowing if it's actually running there, then you cannot rely on them at runtime. So what we then looked at is whether we can still kind of rely on them manufacturing this thing properly while at the same time not having to trust them at runtime. And the way the computing stack currently then looks like is you have this operating system and hypervisor, which are potentially malicious. You have the CPU that you trust at some point, but you don't necessarily trust it now. And so what can you do to actually reduce the trust that you have in the system and actually, still build a meaningful TCB out of this? And so when we looked at this, we asked, okay, when are you actually executing these read parts? How do you transfer control to the untrusted parts? And normally you would have instructions coming from the memory region of your application running on the CPU. And then at some point you get an interrupt. And then this interrupt will have a number. Then the CPU will look, okay, actually I got interrupt number 1. This means I now need to transfer control to the hypervisor. And that's when the code that you don't trust starts executing. So essentially, what we wanted to do was to redirect all of the entry points to the code that you don't trust, such that then, even if you're running on this system where things can be potentially malicious, you could redirect the execution to always be executing code that you trust. And essentially, what this means is that we will now have a cloud service provider managing the cloud. And then when we want to execute on very sensitive data, so they have different levels of sensitivities at the ICRC. There is some data that they are fine, even if it leaks, in a sense. But for some data, they really want to make sure that nothing can happen to it, even if the cloud provider is malicious, for instance. And so, so this solution is mostly suited for now a custom cloud deployment, which is something that they are fine with. And essentially, a cloud service provider will help them set up their own cloud locally in Switzerland, for instance, where they can enjoy some protections from the law. But then at the same time, the ICRC will have some guarantees that the cloud service provider cannot tamper with their execution when they want to. So the way this works is we would modify the interrupt descriptor table such that whenever we want to execute in this sensitive mode, the interrupt will redirect the execution to a special device that we have connected to the server. And then the CPU will start fetching instruction from this device. So now this is how the computer stack will look like whenever we enter this execution mode. Instead of having the full hypervisor and OS provided by the CSP, we will actually be executing temporarily on the device OS. So what do we need to actually do that? Well, the device needs to basically expose a memory region to the CPU, such that the CPU can fetch instructions from the device. And it needs to be able to read the whole memory of the server where it is connected. And it needs to do that to serve basically all of the interrupts. For instance, it needs to be able to do page faults, but also needs to make sure that nothing else is going on that server. And luckily, there are two very nice primitives that are widely available that allow you to do that, which is PCI Express and DMA. So PCI Express will allow us to expose this memory region to the CPU, such that then we can serve interrupts from the device. And it will allow us to kind of give complete DMA access to the whole memory of the system. So this is how we plan to give them sovereignty over their cloud, while still allowing another company to manage their infrastructure and leverage the expertise of this other company. And we need a separate device for this because we envision them to manufacture this device. Like we envision that this device will be produced on a kind of older node from a facility that perhaps they can trust more than the CPU manufacturer. And they would be able then to do key management just on this device. So they just need to then create a TLS endpoint to this device, and then the device will take care of the rest on the computing platform. So it's finally to have this, we need a secure channel from the device to the CPU, such that if there is any other device or any physical attack on the system, we are sure that the CPU is getting the instructions from the device without being tampered. So luckily PCI Express, the new versions, as Cedric was mentioned before, they allow for keys to be set up such that you can have link encryption and authentication. And the nice thing is that this device will kind of have visibility over what's happening on the PCI Express bus. And if there is anything else, any other communication going on there from any device that we didn't specifically approve, then we will know that something shady is going on because all the communication should start from the device that we have there. So to conclude, essentially, under the threat model of the ICRC, we cannot trust TE manufacturers at runtime because they could be compelled to provide access or to compromise the system, essentially. And our device is kind of able to build a smaller TCB while still allowing the cloud service provider to manage the whole infrastructure for the ICRC. Yeah, and if you have any questions, I guess now it's a good time. Yeah.
Let's thank the speaker. So, any questions? Yeah.
Cool. Yeah. Yeah.
Yes, because here you mentioned ICRC facility but managed by a CSP, but that was the case of the data breach that happened a couple of months back in January. It was ICRC material on a Swiss sovereign cloud provider, not a major cloud provider like the GAFAM. And so to which extent your device would have prevented this?
So the company itself wouldn't have had access to the data. So you would have had to compromise the ICRC directly at that point. You would have had to leak.
But that's what was done actually. It was not the cloud provider that was hacked. It was
the cloud provider
specifically.
Right. It was so it was a third company that they were contracting that was hacked. Yeah.
Okay.
So interesting work. What about scalability? How many of these devices do you need for how many compute nodes and things like this? I mean, how does this work at the scale of the cloud?
So yeah, you need one of these per server that you have, essentially. We didn't really think about that yet. We are just trying to build a prototype at the moment. But yeah, to have something meaningful, you would have to have it physically connected to the server where you want to execute at that moment, basically.
That's another question, because for major cloud service providers, basically, if we need a custom device for our hardware that we are going to use, that's kind of equivalent of renting the hardware ourselves, right?
Yeah. So
I mean, it makes complicated from a commercial point of view to have this kind of negotiations.
So anyway, we don't envision this to be this device to be connected on the Azure cloud, for instance. I don't know if that's what you were hinting at. But we still want, so let's say Microsoft will help them build a cloud in Switzerland where they can, where they have some immunity in the law, and for instance, police cannot enter their facilities, right? But then even then, if Microsoft is managing this cloud for them, Microsoft will have access to, and I'm picking on Microsoft here, not because they are bad, right? But so they will have access to the data there, and they will help them. They will give their expertise, and they will help them manage this infrastructure. But at the same time, then they will not have access to the most sensitive data that they are managing there. Yeah. I don't know if this answers your.
Yeah, just a clarifying comment here. So this is, of course, a pure research collaboration.
Yes.
We are looking at potentially solving a problem with research. This is nothing that will be implemented in any product anytime soon.
Right. Let's take one last question.
So thanks for the talk. I was wondering, do you actually see a way for Intel to take themselves out of the trust path, like give a very small primitive that shows you that the hardware is the one you expect, but then don't have to contact them all the time to verify attestation? Like, do you think there's a way for them to get out of the loop at some point?
I think possibly they could redesign the whole protocol to accommodate for this. The problem is that they of course see themselves as trustworthy, right? So in a sense, I guess they never had an incentive to remove themselves from the loop. So there are some other attestation protocols that they have, like these data center attestation primitives. But even then, or even AMD SCV, you could do the same attacks. Like at some point, they know some key material, or they can extract some key material, so you end up having to trust them at runtime. Like on some of these protocols, it's not obvious, but if you look for it, you will see that they actually could have access to some of this key material if they wanted to.
All right, let's thank the speakers once more.